Lesson: Addressing Bias and Fairness in AI Security Models. Addressing bias and fairness in AI security models is critical in ensuring that these systems are not only effective, but also equitable and just. As AI technology becomes increasingly embedded in security frameworks, it is imperative to recognize and mitigate biases that may lead to unfair or discriminatory outcomes. Bias in AI can originate from various sources, including the data used to train models, the algorithms themselves, and the human designers who build these systems. Therefore, addressing these biases requires a multifaceted approach that combines technical, ethical, and legal considerations. Firstly, understanding the types of biases that can occur in AI systems is essential. Bias can be introduced during data collection, where datasets may not adequately represent the diversity of the population they are meant to serve. For instance, if a facial recognition system is trained predominantly on images of individuals from a particular demographic, it may perform poorly on individuals outside that group, leading to errors and potential discrimination. This issue was notably highlighted in a study by Buolamwini and Gebru, where commercial AI systems exhibited significant gender and racial bias, performing worst on darker-skinned females. To combat data bias, practitioners can employ data augmentation techniques, which involve artificially increasing the diversity of the training dataset. This can be achieved through oversampling underrepresented groups or generating synthetic data that mirrors diversity. Additionally, using diverse and comprehensive datasets from the outset is crucial. The Open Images dataset, for instance, is a large-scale dataset that offers a more balanced representation across various demographic groups and can be a valuable resource for training fairer models. Another practical tool for addressing bias is the use of fairness-aware algorithms. These are designed to incorporate fairness constraints directly into the model training process. One such algorithm is the Fairness Constraints Framework, which allows the inclusion of fairness metrics like demographic parity or equal opportunity as part of the optimization objective. By explicitly defining what fairness means for a given application, developers can guide the model towards more equitable outcomes. Evaluating AI models for bias is also crucial. This involves measuring the performance of AI systems across different demographic groups to identify any disparities. Tools like IBM's AI Fairness 360 provide a comprehensive suite of metrics and algorithms to assess and mitigate bias in machine learning models. By using these tools, practitioners can gain insights into how their models perform across various groups and take corrective actions if necessary. Beyond technical solutions, addressing bias and fairness also requires an ethical and legal framework. Professionals must be aware of regulations such as the General Data Protection Regulation in the European Union, which outlines requirements for fairness in automated decision-making processes. The GDPR emphasizes the right to explanation, meaning individuals have the right to understand how decisions affecting them are made by AI systems. Incorporating ethical considerations into AI security models involves engaging with stakeholders to define what fairness means in specific contexts and developing guidelines that align with these values. This participatory approach ensures that the systems we build reflect the values of the communities they impact. Furthermore, organizations should establish governance structures, such as ethics boards, to oversee the development and deployment of AI systems, ensuring accountability and transparency. A case study highlighting the importance of fairness in AI is the COMPAS algorithm used in the U.S. criminal justice system to predict recidivism. A ProPublica investigation revealed that the algorithm was biased against African American defendants who were falsely flagged as future criminals at nearly twice the rate as white defendants. This case underscores the real-world consequences of biased AI systems and the need for rigorous fairness evaluations. Statistical parity and disparate impact analysis are additional frameworks that can be applied to assess fairness in AI systems. Statistical parity requires that the probability of a positive outcome should be the same across different demographic groups. Disparate impact analysis, on the other hand, examines whether decisions disproportionately affect a particular group, even if unintentionally. These frameworks provide a structured approach to evaluating fairness and can guide developers in fine-tuning their models to reduce bias. Finally, ongoing monitoring and auditing of AI systems are essential to ensure that fairness is maintained over time. AI models can change in behavior as they are exposed to new data and environments, potentially reintroducing biases. Regular audits, using tools like model cards and datasheets for datasets, provide documentation that captures the intended use, performance, and limitations of AI systems. This transparency facilitates accountability and continuous improvement in AI security models. In conclusion, addressing bias and fairness in AI security models is a complex but necessary endeavor. By leveraging diverse datasets, employing fairness-aware algorithms, and using comprehensive evaluation tools, professionals can build AI systems that are more equitable and just. Moreover, integrating ethical and legal considerations ensures that these systems align with societal values and legal requirements. As AI continues to play a pivotal role in security, prioritizing fairness and bias mitigation will be crucial to building trust and ensuring that these technologies benefit all members of society.